You think that's air you're breathing? It's time for math with Mr. Troy. Another way to solve systems of equations is to use the method of substitution. Now, while this particular system of equations could be solved using either substitution or elimination, I'll use substitution to solve it as a way of illustrating with an easier problem. To solve by substitution, you want to start by taking whichever one of your two equations is easier and isolating a variable. Now, when I say easier, I mean easier to get one of the two variables by itself. I could also have solved the top one for y, but I do think that the bottom was a little more simple. Then I'm going to take that and I'm going to plug it into the other equation. I'm going to replace the y with an x plus 2. X squared minus 2x plus y equals 8. Now what I have here is a quadratic equation, and that's something that will happen somewhat frequently. I'm going to solve that, but there's going to be a little bit more. So this particular quadratic equation simplifies down to x squared minus x minus 6 equals 0, which when I factor, I can see has the solutions x equals 3 and x equals negative 2. But I'm looking, because of the way that this question is posed, for x values and y values that make these equations true. So if I plug in x equals 3, I'm going to get y equals 5. And if I plug in x equals negative 2, I'm going to get y equals 0. So this system of equations has two solutions, the points 3, 5, and negative 2, 0. To see why that is, let's look at a graph. To desmos. As I can see, graphing these two equations gives me one parabola and one line. Those two figures happen to meet at the points negative 2, 0 and 3, 5, just as my equation solving suggested. Now, you will know that you're looking for coordinate points, x, y, because the initial problem is given in both x and y. You will know that you're looking for more than one because you get a quadratic equation. You do want to plug those answers into both of the equations to make sure that they work for both equations. All right, now here's one that's a touch harder. We need to start by getting one of our variables by itself. And what makes sense to me is to get y by itself. So y equals negative 2x plus 2. Plug that into the next equation. X cubed plus 1/4 times negative 2x plus 2 squared minus 1 equals 0. So what I've done here is I have replaced y with negative 2x plus 2. That's the substitution. Now I'm going to FOIL out and see where I've gotten. When I FOIL that out, I notice that everything inside these brackets is divisible by 4, so I'm safe to divide that by 4 to simplify that fraction. X cubed plus x squared minus 2x plus 1 minus 1 equals 0. And that simplifies down to x cubed plus x squared minus 2x equals 0. Now I just solve this like any other equation. This one might have as many as 3 solutions because it's an odd polynomial function. I think you should always start by factoring if you can. So x times x squared plus x minus 2 equals 0, or x times x plus 2 times x minus 1 equals 0, which gives me 3 x values. X equals 0, x equals -2, and x equals 1. To find the y values, I'm going to plug into either the original bottom equation or perhaps this equation right here. This one's a little bit simpler for finding y values. Now you do want to be careful. You only want to do that if you are relatively certain that you haven't made a mistake going from here to here, or that you haven't changed the domain going from here to here. So when I plug in 0 for x, I get 2 for y. When I plug in -2 for x, I get 6 for y. And when I plug in 1 for x, I get 0 for y. So this system of equations had 3 solutions: 0, 2, -2, 6, and 1, 0. As always, you can check by graphing. Now, I don't know the name of this red figure here, but it's pretty neat. And it is intersecting that blue line at 3 separate places. Sound the alarm, I accidentally described something as neat. All right, now this third problem gives us a bit of a conundrum. Do I want to plug x into the top equation, or do I want to plug y into the bottom equation? I think I would rather plug in for x because it's a binomial. So I think what I'm going to do is y equals y squared minus 4y squared plus 2 times y squared minus 4y plus 4. And this is going to take quite some foiling, so I'm going to let movie magic do that. I think a common instinct is to multiply all that out and then to get to this y equals and be kind of confused. Because you're not used to seeing y in this position, you're used to seeing x in this position. So what you want to do is you just want to get the y by itself, or sorry, get rid of the y. And then solve this like we would in a polynomial unit, but use y's instead of x's. So all of a sudden, we're back here again. And we start by plugging things in. And we can see that this one doesn't work. So we keep trying until we do get something that works. Sorry, that would be +2. So we know that one of our zeros has to be y equals 4. Now I know from looking at this equation that when y equals 4, x equals 0. But don't make the common mistake of saying 4, 0. This is 0, 4. So 0, 4 is one solution to this system of equations. Unfortunately, the other solution to the system of equations is not something that we currently have the tools to figure out. Let me illustrate. We already know that 1 is not a rational 0 because it was the first thing we tried. So the only thing left to try would be -1. And when I plug that in, it just doesn't work, which means there are no other rational zeros. Now, why is that a problem? Well, if we got all the way down to a quadratic, we would know where to go from there. Unfortunately, what we've left ourselves with is y cubed minus 4y squared plus 2y minus 1 equals 0. So, unless you know the cubic formula, which I suppose you might, we'll need to wait till later to find the rest of the solutions, or the other solution to this problem. And that's okay. Here's a graph of what that system looks like. We can see our solution here at 0, 4, but this irrational solution we really can't be sure of quite yet. I'd like to finish by illustrating that you can use substitution to solve a 3x3 system of equations, but that you might not choose to. We would want to start by isolating whatever the most convenient variable is. So let's say for this one that is that y equals z. Then plugging into the other two equations, I would have x plus z minus 3z equals -1, and negative x plus 2z equals +1. This simplifies to x minus 2z equals -1, and negative x plus 2z equals 1. Well, what do we notice here? These two equations provide us with redundant information. Each one tells me that x is 2z minus 1. I also know that y equals z. So this system of equations just doesn't provide enough information for me to get a one single answer, so this one must be infinitely many solutions. Just like we have done with elimination, that tells us that if we let z equal a, that solutions would look like a for y and z, and 2a minus 1 for x. I'm plugging in a there. Okay, everybody, I hope that video is helpful for you. Something that you've done since Algebra 1, but probably need a little bit of practice, and then a new application for it, solving nonlinear systems. Don't get too scared by the fact that we only knew how to find one of the solutions to that third system of equations. Although it is October, so if you want to get scared, that's okay. Have a great day.